First of all, what are the objectives of the project that I'm going to talk about? First, it's, mainly we wanted to improve and create a layer that would contain the urban regions available, that are, basically a way to define the regions in Catalonia, which is the country I'm based on and the company is based on, find the regions that are urban and populated, basically urban regions. The definition of urban region is not very clear, it's not defined. Basically, it's more or less 3, 4, 5 houses together in the same region. This excludes isolated houses, and this excludes, how do I say it? Basically factories and similar buildings like that. It's only for residential use and good enough congregation of that. So the ICGC, the Cartographical and Geographical Institute of Catalunya, provides a layer that includes this information, but this is an example of that layer. As you can see, it's not very precise. It has many flaws, it's not precise at all. Basically, for example, in this case, you can see there's quite a bit, a place, very clearly a residential zone that is not covered by this layer. And in here as well, you can see there's quite a big place that is industrial that shouldn't be in this layer, but it is. So, although we have this layer as a good starting point, it was definitely not good enough, and we tried and improve this. To improve this, we decided to use machine learning and convolutional neural networks, and that is what this talk is about. Oops. First of all, a bit of a background. For those who know a bit about machine learning and these kind of problems, you may have seen that this is clearly an image segmentation problem. There are many different kinds of image segmentation. There's semantic segmentation, there's instant segmentation, a mix of both, which is called panoptic segmentation. In this case, we just interested in semantic segmentation, basically if a point is or is not an urban region. And we are interested in the more basic case of this, which is binary segmentation. Basically, it is urban or is not urban, true or false. We did our research a bit, and we found that there are some models. For those who attended the first talk, I don't know if first or second talk of FOSS4G yesterday, they talk about segment anything model. We also find it, we researched it a bit, and as they said, it's not a good fit for this kind of problems. Geolocated data and geographical data really does not fit this model's strength very well. As they said, the background and the foreground are not clear at all. Some things are occluded. It's not really the good tool for this project. So what we decided to do is to create our own tools, our own algorithms, more or less. So we decided to use convolutional neural networks and machine learning. First of all, a bit of background on what convolutional neural networks are. Basically, it's a convolutional neural network may have many different parts. The main one is the convolutional layer. That's why the name is what it is. So basically, it slides a kernel, or basically a filter, across the image and extracts information one pass after the other. This seems a bit abstract, but it's the beauty and also the pain of neural networks. You don't know what it does, but apparently with enough data it does it well. And this is an architecture that has been proven to work very well with working with images. So this is the first step, the first layer of the model. The next thing is an activation function. The thing with machine learning is that if you know a bit about it, it's just basically only matrix multiplication. So you're taking the data, matrix multiply it, add some values, and return it. And for those who know a bit of math, you will know that a sequence of matrix multiplication at the end of the day is the same as just having one big matrix multiplication. So you end up with no complexity at all and no ability to learn anything. So that's why you need to add an activation function. In this case, we used ReLU, which is rectified linear unit, which basically is just taking the positive numbers and leaving them as they are, and the negative numbers going, well, flattening them out and keeping it at 0. This enables us to have non-linearities, which are basically functions that are non-linear, functions that are not linear, and enable the model to learn more complex problems, which is this case. And also, the last important part of our specific convolution, our specific architecture, are the pooling layers, which are basically the layers that are in charge of downscaling or upscaling the images, because as you will see in the next slides, our network basically compresses the images down and then enhances them back up. So we need a way to increase and decrease the size, and the way that that basically the paper set that works the best is max pooling, which is taking a 2 by 2, in this case square, and boiling it down to the maximum value between all those values. So these are the main building blocks of the architecture we're using. And let's talk about a bit the architecture itself. This is what we used, which is called a UNet architecture. UNet, because as you can see, very much like a U, it seems like a U, so UNet, not very creative. And basically the idea is to have the image come at the top. It applies some convolutional, some convolutions, applies some activations, and then you start to downscale it. You reduce the size while increasing the number of layers that it has, until you get to a very, very small but large amount of images. And with that information, you then upscale it back until you get a full image, which, if we've done everything right, should contain this segmented data. So in more conceptual terms, this would hopefully be the first part of it, would encode all the original image, well, basically trying to understand what each pixel means, and boiling it down to an understandable and compressed data that it can read. And then with this compressed data, you explode it back up and create an image with the same size as the original, but only containing the sections that are, in this case, that contain urban regions. So this is basically, in a big picture, the architecture that we're using. It has a bit more depth to it. You usually also take the previous step with the same size and put it back on, but it's details that I don't think matter much in this case. So with this in mind, this model in mind, let's talk about the data set that we used. There isn't a data set for this, of course. This is a very specific problem that we have, so there isn't an active data set. So what we figured out we could do was, well, find the parameters that would, in our belief, in our best of knowledge, would contribute to being able to determine if something is urban or not. Of course, the orthophoto is very important, as it's basic information you need to know. And DVI, which is the index that tells you how much vegetation there is in one particular spot is also something that could matter a lot, because when there's buildings, there isn't vegetation. Also, the infrared imagery, the same as the NDVI, basically more infrared. Well, it varies depending on the type of floor there exists. And also a layer which is the buildings, the shape of the buildings itself that are known to be around there. As the output, well, we wanted to have the urban regions. We have this layer, but as I said before, the one that ICGC provides is faulty, is not correct, so we couldn't use it as it is. We had to improve it. And that's, well, basically what we did. We took 5 regions across all Catalonia, and regions from, well, yeah, 5 regions, 12 by 12 kilometers in size, and manually improve them. This is the examples I showed before. In these cases, very clearly a spot that is missing, so we fixed it with the spot not missing anymore. And the same in here, removing the parts that shouldn't be here. This basically was a lot of work, handwork, that had to be done, but thankfully the idea was that if we could do this in a small section of Catalonia, just 5 12 by 12 kilometers regions, we could train this AI for it to apply this knowledge to the whole Catalonia. And, well, this is basically what we've done. At the end, we had these regions, and we needed to create a data set out of it. To create the data set, basically what we will need is a series of images, all these, as I said before, all these input, like all these layers, plus the output we wanted. So we took these 5 regions and sampled random spots with random zoom levels between some ranges, of course, and extracted all this information. To do this, basically what we created was a QGIS project with all the information, all these layers, all very precisely put it in place with the styles that we wanted, and published them in a QGIS server so that it can be easily looked up by a Python script. So, and then this Python script just queried this server with these random positions and random zooms, and took out the images and stored them locally in disks for later be used to train. For this specific case, we took an 80-20% split for training and validation. I don't know if you're familiar with the concept, but basically you need to reserve a bit of information for you to test how the model is doing, because if you don't, maybe the model could end up just memorizing the data you give it and not learning enough for it to extrapolate to areas that hasn't been seen before. So we reserved one of these 5 regions for validation, and the other 4 we kept for training. And okay, so let's talk a bit more about the model itself, the specifics of the model. As I said, it's a UNet architecture with convolutional neural network like layers. As I said, our specific model had 12 layers, 6 for the decoder, so 6 encoding going back down, and 6 more to blow it back up to the original size. We use binary cross-entropy loss, which is a very common, very common loss for this kind of problems, as it's binary at the end of the day, and it's the state of the art in this case. And we used Adam, also a very common optimizer, which is basically the part that tunes all the parameters of the model for it to improve over time. And also, in order to keep track of how the model was performing, we added some metrics like accuracy, precision, and recall. I'm not going to go in depth, but mainly we're going to be talking about accuracy, which is basically the percentage of pixels basically the percentage of pixels that it correctly identifies as urban or not urban. A bit about the training itself. As you can see, for anyone that is familiar with neural networks and training neural networks, this is very good news. This is the training for, well, this is the evolution of accuracy over time while we train the model. What we see here is both the blue and pink lines are the training and validation accuracy. And as you can see, they're both one right on top of the other. This is very good. This means we don't have neither overfitting, neither underfitting. So we're very good, like in track of having a very good model. And also the highest accuracy we managed was 98.66%, which is also very, very nice. The same graph, but for loss. Loss is, as I said, the thing that we use to keep track of how the model is doing, but in more technical terms. So it's the thing that it's exactly used to optimize all the little parameters of the model. And as you can see, the same thing as the accuracy. Very good results. Accuracy with loss with train is almost equal as loss with validation, which is very, very good news. And finally, with the final model we took, this is the results we got. The average accuracy was around 98%, which is very good in this case, considering it's imagery, and there are a lot of pixels in there, so fairly good result. And as you can see, most of this is the validation data set, most of the validation are above 90% accuracy, which is very, very good. As you can see, though, there's a couple, well, in fact, 3 outliers, very clearly outliers here, below 70%, around 65% accuracy, which were a bit strange, so we had a look at it. I'm going to show you 2 of them. The first was this one, and this is the prediction from the model. This was what it was supposed to predict. And as you can see, it predicted much less than it should have. But if you take a closer look at it, the zones that it should have predicted but didn't predict, in the map, we can see that are actually not supposed to be regions of urban regions. This is a spot we missed while we were improving the ICGC layer. So basically, the model improved our own data set, so it's very nice. This was quite a big relief, because it basically only highlighted the spot that should be highlighted, which is that little urban area in there. And the same happens with this spot. We had also, the test was overreaching, was including some industrial areas that shouldn't have been included. It also included a bit of forest, which shouldn't have been included, and the model predicted it very well. So, very good results so far, and to test it a bit more, we took the model and made it predict a large portion of Catalonia, which wasn't neither on the training nor the validations data set. And these are the results. There are some, well, we picked some of these results. This is, for example, one specific region. This is what the original ICGC layer included, which in this case was correct. And our model fairly well predicted almost perfectly what it's supposed to be, also excluding a bit of forest in the middle, which is also nice. So, good results in here. Another example is this one. The ICGC layer clearly missed quite a lot of houses around here and there. So, let's see how the model did. And in this case, also very well. It's not as well defined as the other ones, but it was good enough. And we can also see there's a couple of houses in there. I don't know if with the projector it's very visible, but there's a couple of isolated houses that the model also predicted that probably shouldn't be there. And this is a problem we found. Also in the next example, the model tends to overpredict small houses, which shouldn't be recognized as a urban area. At the end of the day, single houses are not a urban area. And this is a clear example. In this case, these 3 scattered houses are just scattered houses, but the model identifies them as urban area, which definitely shouldn't be. So, very in general terms, very good, but as you can see, some mistakes. To recap, as you may have seen, we are very happy with the results. These are very, very good results well, we didn't expect this good of a result. It even managed to improve our own hand-written, like hand-improved regions, which was very nice to see. Of course, it improved the ICGC data, which was the original objective, so good thing on that. And we end up with a 94.52% accuracy. But as I said, it also overpredicted a bit of isolated houses, which may be an issue. But as you may have seen as well, the output is very blurry, is not very defined. So for sure there needs to be a bit of post-processing for it to be completely useful in a fully production environment. And in this post-production, maybe this post-processing, we could find some algorithm for removing these isolations. It's probably fine, but well, we would need to work a bit more on it. But yeah, basically, very good results in general. And well, going forward, of course, even though these very good results, there's some things to improve and there's some things to try. As at the end of the day, machine learning is very much trial and error. We could just keep tweaking the parameters, keep tweaking a bit the architecture, and find if it improves the model. Of course, trying different architectures could be a possibility. And of course, it's machine learning. More data always will help. So if we hand improve some more data and share it with the model, maybe it could improve. And of course, better data, which means not committing the mistakes we've committed with the correction of the layer, because as you may have seen, well, there were some issues in there. So yeah, this is basically it. Thank you very much. If there's any questions, I'll happily answer them. And yeah, thank you very much.